Another long introduction. Were you ever a Yale postdoc, Chris? No, you never.
I think that defines me.
There's no introduction at all.
Yeah, no, forget it. You're on your own. No.
I should not give. Yeah, should probably not give a talk.
Yeah, okay, no, that's right. Chris Haber from Georgia Tech. Take a look.
Can you hear me? All right. So we'll take a slightly different spin this afternoon. So the goal of this presentation is actually not really to talk about numerical modeling methods. You'll hear more about that tomorrow, I guess. But it's to go beyond the continuum scale approach and try to see where we do things correctly, where we do things not so correctly, and when things can be fixed up in a relatively simple way. We'll talk more about this later. I don't work much on the mantle, as a disclaimer, but I'm fairly interested in understanding how multiphase and single-phase fluids propagate through porous media, and how this controls, for example, chemical transport, heat transport, and other things. I want to talk to you about those. And the point of this presentation is really to reflect. It's more like a discussion, so interrupt me whenever you want. But to reflect on sometimes the loss of information that can happen when we average things out. So the outline for this presentation is to talk about different kind of problems, and we'll start with multiphase buoyant transport. So that goes along what Majid was talking about 2 days ago, about bubble transport, buoyant transport in this case, of bubbles in a saturated porous media. And then we'll talk about rheology, not rheology for the mantle, unfortunately. I work more on magmatic processes and magma chambers. But the deformation of crystals, of a crystal network or a combination of crystals in silicate melt is of interest in many other aspects. And I'll show you that's an example where you can correct some of the mess associated with the multiphase exchange of stresses in a relatively simple way. But as we move along, the simple problem of solute transport, even in a non-reactive porous medium, gets already a little bit more complicated, as we will see. And I will finish with the simplest problem in the book. It's thermal convection for a single fluid in a homogeneous porous medium, and show you that there's some problems also with the continuum approaches, and that one needs to be a little bit careful. So there's a gradation in difficulty in how, from these three processes, on how you should basically think of doing the continuum approach. So I want to start with something that was reflected on the first day, I think, by Dan McKenzie, is that when you downscale and you start to look at a system as the sum of different components that really interact through interfaces, for example, things get complicated. And very often the intuition that we build from our everyday life starts to fail. So I will try to show you this very simple example that most of you probably know of. It's a case where I have bubbles. I don't remember the number. It was probably 50 or 70 bubbles. They're buoyant. They want to rise to the free surface on the top. And those bubbles will interact as they move. This is a relatively low Reynolds number flow. I don't remember exactly the value, but it's probably around 1. And you have two conditions. The first case here, the conduit is aligned with gravity. Okay? And this is exactly the same case, same number of bubbles, the same vertical distance to propagate, but now I introduce the tilt between the conduit and the bubble propagation. As a warning, there's some problems of post-processing in the visualization, so don't care too much about that. It has nothing to do with the calculation themselves. So here I will be solving a Navier-Stokes equation. The bubbles have a surface tension, so you'll see them deforming, interacting with each other. And we also parameterize coalescence from experiments with Helge Gunnerman at Rice. So what I want you to look at, specifically, as I will show these two movies, is how bubbles talk to each other. They like to talk a lot to each other, as you will see, and that introduces some patterns in terms of flow. All right, so let's have a look at the first one. So what you'll see is that the hydrodynamic interaction between bubbles leads to a decent amount of left and right dynamics. And if you were to calculate or measure some kind of correlation distance for the flow, it will be not much longer actually than the length of a single bubble. So it's fairly chaotic. And if you just introduce a tilt, sure.
There's a lot going on.
Yeah, sure. Oops, let me move the mouse so you can see.
This is a computation rather than experiment, right?
Yeah, that's computation, yeah.
Is that lattice Boltzmann or the?
Yeah.
What equations have you solved?
Navier-Stokes and surrounding fluids, and in the bubbles here, the ratio of viscosity is is 0. So the viscosity of the bubble is 0. So I'm not solving the pure dynamics, but I'm solving the pressure evolution and the deformation of the interface. So there's surface tension.
And that problem like gas diffusion.
No. There's no growth of bubble by gas transport. There's no exchange of mass between the two systems. Yes, there is.
And is there a grid underneath? Is it?
Yes, there's a grid. Yeah. That's the reason why we had to introduce some parameterization for coalescence also, to make sure that we can basically solve it properly. So the main point I want to illustrate with that.
The surface tension must be rather weak since they're not spherical.
Yeah. Or think of it as a bubble being relatively large, if you think. So they deform as they move up. Yeah?
Why do you have at the end a layer of liquid between the bubbles at the very top?
Oh, I finished the run. They will basically pop up to the surface as well. You need to drain them out. And we compare that with experiments, actually, that were run by Helge Gunnerman to get the right drainage rates. All right? So the point I want to make here is to contrast that with what happens. This is fairly famous, actually. There was a paper in 1920 in Nature, actually, talking about these processes. Exactly. And when he was working with red blood cells, actually. And so just by introducing a tilt in the conduit, you start to organize the flow rather more, and actually you have now the return flow on one side and the upwelling on the other side, so it's much more efficient. The main point of this calculation, I don't think they have much of a scientific value, to be honest, but the main point here is to show you that here you have a greater distance for the bubble to travel to the free surface on average, and they go faster. So there's lots of interactions. The interaction between bubble is not as trivial as we can think of. And that's kind of the main point I want to address throughout this talk, is when you go from a multi-phase system that contains heterogeneities, sometimes going from the granular scale, the scale where you have the different components expressed, to a more continuum approach is not always trivial. So, well, it's never trivial, to be honest. So one thing that was discussed here a few times was this reactive infiltration stability for two-phase system, especially the first day, as one of the processes by which you can form this channels, the Danae channels, one of the two processes. And here, one question I was curious about was what happens now if you have three phases? So two immiscible fluids and a solid. And the non-wetting fluid, now everybody knows what the non-wetting fluid is, contains, for example, some reactant. So this problem here is not really a chemical problem. I was interested more about heat transfer. But imagine that I'm injecting bubbles. They're buoyant. They have a lower viscosity than the surrounding fluid. They're organized to form those patterns. These are fingering patterns. It could be viscous fingering or capillary fingering, depending on what kind of regime you're looking at. And initially, they contain some excess enthalpy. The system, the solid, is very simplified. I'm not looking at complicated reactions, but I'm assuming that the solid is at its melting temperature. So I want to look at the feedback between transport of buoyant bubble that are hot, for example, and melting, the evolution of the porous medium. So this is a system in two-phase. We know that if you have reactions that enhances dissolution, the transport will be favored by more dissolution. So if you start to partially dissolve a certain region, then you have an enhanced solute flux or reactive flux to that region, and you form this kind of wormholes or reactive infiltration stabilities. So the question here is what happens when it's a non-wetting fluid that does the trick. So before we do that, for some of you who are not really familiar with these types of problems, this is fairly similar to what Manjit was showing. Here, what we're doing is just to show you what happens when you inject a buoyant non-wetting fluid at the basis that this is just an inlet of a fictitious porous medium. After a certain pressure is built up, then you have a penetration. You need to overcome this capillary entry pressure, and you form those fingering pathways that start to propagate to the system. Yes?
What is in the porous medium when
It's a wetting fluid I'm not showing, yeah. Yes, there's, it's filled with it's basically a drainage kind of problem in this case, a buoyancy drainage problem. All right? So the main point here is that if I have a finite system like this one, once I establish those pathways and they percolate through the system, I have a continuous path for this non-wetting fluid to transport through this small medium. And that can really emphasize or enhance actually the transport of this non-wetting fluid. That will change all the properties of the system. So I'll show you a little bit the background that what we've done with this problem. I'll go very quickly in the next few slides. We only allowed a fraction of the solids to be reactive. And we don't want to dissolve the whole porous medium. This, I might Okay, so these are some of the equations that at the pore scale, I don't want to show them too much, but there's one thing I want to really emphasize, is that you've seen this mass conservation equation or some versions of those mass conservation equations many times so far, but we don't have the volume fractions, again, because we look at the pore scale, okay? So that's the difference. It's a slightly difference in principle. You have, that's the definition of the stress. I put the gravity in there. That's the surface tension problem. This is the viscosity ratio between the fluid. That's the bond numbers, that's surface tension. And there's a difference in density between the two fluids. Okay? So, more interestingly, this is what it looks like when I do those calculations. So again, I'm injecting this buoyant non-wetting fluid in the system. It naturally forms these fingering pathways. As those fingering pathways form and as the non-wetting fluid basically moves up, it loses some heat sideways, so heats up the wetting fluid, and there will be some reactions with the part that can melt of the solid, okay? That's the idea. But we can track the different variables. So the first thing that we were interested about is this is very complicated and not really tractable if you want to upscale that very easily. So can you simplify those channels, for example, by something that is much more easy to deal with, such as an annular flow, for example, okay? So imagine you represent those main channels, those finger instabilities, as a channel flow. So you have the non-wetting fluid at the center. You have some wetting fluid on the edges. And here we'll make a lot of assumptions that should not work. First of all, we'll assume that there's a fixed temperature here, high temperature at the inlet. As you move upwards, the temperature will start to cool down because you'll diffuse sideways. We'll assume that the walls here stay isothermal. That might not be too bad of an approximation, especially if you assume that there's some latent heat involved, and you know we have a very simple melting kind of problem in the numerical calculations. And if there's only a very small amount of melting or dissolution, whatever you want to call it, then those walls should not move too much. So if that's the case, and that's a very rough approximation, then you know that the temperature profile as you move away from this should be exponential, and that the length over which it will decay, the folding length, will depend on the Peclet, 1 over the Peclet number, basically the advective to diffusive ratio. And so that the heat flux, radial heat flux, will also depend on the same kind of properties, and so forth. If you think that the amount of dissolution or melting is proportional to the radial heat flow, then you should have a porosity profile after a while that should look a little bit more like an exponential. So it should not work because those are a lot of assumptions and it doesn't really look like the real case, but it works pretty well. So what you're looking at here is one of calculation with fairly high Peclet number. This is not really the porosity. We don't melt everything. It's normalized. So this is the maximum porosity when I melted everything I could melt. And this is when nothing has melted. So it's the same state, the porosity remained the initial porosity. And what you find here is that here we saturated the melting, but in a region where it's not saturated follows this exponential law. Yes?
Have you now got 3 fluids, melted solid?
No, we assume that the wetting and the melted solid is the same thing. It's very simplified.
Thank you.
So think that the wetting fluid and the solid are it's a pure substance kind of problem. Right? So we conducted that for different kind of ratio of advective to diffusive flux, and to test that if the prefactor or the folding length depend on the Peclet number, it works pretty well. So to me, that's fairly encouraging. That means that you can simplify the system to some great extent already in terms of if you wanted to do some exercise for upscaling to some extent, okay? The second question that we were interested about is to look at the effect, and this is a very simple problem, looked at the effect, how deep the excess enthalpy can be carried into the porous medium. And obviously that depends on the Peclet number, the ratio of advective flux at the pore scale to diffusive flux. So these are 3 cases, you know, when the advective flux is relatively large, as it gets smaller. These are the isotherm in the system. Obviously, it correlates fairly well with what you would guess. The last point actually is not really trivial, and I think that's fairly interesting. So that's what I want to talk to you about, and that's basically answering the problem of this reactive infiltration stability for 3 phases. As melting or dissolution takes place, the porosity increases, and therefore the permeability should increase it as well. But what we observe actually is a decrease in the efficiency to transport the non-wetting fluid. And I'll show you why. So these are 3 calculations that are in all point identical. The only difference here, think of a melting problem. I increase the latent heat here, decrease it a little bit here, not a little bit, an order of magnitude, and another order of magnitude here, okay? So it gets more and more easy to melt here compared to here. When melting is negligible, then those pathways are stable. And there's no reason for them not to be stable as long as I provide enough flux of non-wetting fluid. When there's a little bit of melting, you don't need much, things look very different already. And when there's a little bit more melting, and there's not much melting here, we made lots of tests, you don't need much melting actually, maybe 1%, maybe less. Then these channels that were stable and able to transport fairly efficiently in the non-wetting fluid are broken into slugs and bubbles. And those bubbles can remain capillary trapped, or if the viscosity contrast between the two fluids is relatively large, viscously trapped into the porous medium. So effectively, you had a system here that was much more efficient at transporting the non-wetting fluid than what you get here, even though the permeability increased. And just because the permeability is just a two-phase property, it's not a three-phase property, right? In some ways, you can identify it's a very different regime to some kind of Rayleigh plateau instability. If melting changes the geometry of the porous medium, now you have a little bit less solid confinement, and that allows some wiggles that could basically destabilize those jets. Is there any question? Yeah, Majid?
So are you assuming here in your calculations things like wettability, contact angle
Yeah.
remains the same?
Yeah, yeah. We don't have a dynamic contact angle in this case, if that's answering your question.
No, also you,
Oh, yeah.
temperature doesn't change.
Yeah. It doesn't depend on temperature, and the two different solid phase, the fictitious solid phase, the one that is allowed to melt and the one that is not allowed to melt, have the same surface energy. There's no difference.
And does the vertical size of your domain play any role? I mean, if you took your low step number case, you twice the length, do those channels start to pinch off?
No, it will just take more time to basically build those fingers. They're slow to build, actually, especially if the viscosity ratio is such that the wetting fluid is much more viscous than the non-wetting fluid. You just need more to wait to get more non-wetting fluid in the system to build those. The spacing between channels can organize to find a steady state length. I'm not saying that the distance between these two fingers will remain necessarily the same if I have a bigger domain. That could change a little bit. Any other question on that?
Did you explain, or are you going to, why that is the case?
Why that? What?
Why this is the case? Did you explain it? So I missed it.
Why the spacing could change?
No. Why these things pinch?
Oh, yes. I think I did, but I will do it again. The idea here is that as you change the pore space by increasing the amount of space that you have, the confinement, I'll come back to the confinement in more details, how it plays a role. What I call the confinement is the fact that the solids confine the space available for the non-wetting fluid. And that has a huge role in the stability of the fingering pathways. For example, if you try to have a liquid thread that is infinite in length and you don't have any confining, you don't have solids around, it's impossible to stabilize. It will break into a continuum of droplets, right? So this is the same problem. If you now put some solid bounds to it, it's possible to stabilize it for a much longer time and even to stabilize the systems. So the solid has a huge role on the ability to form those fingering pathways. Any other question on that? No. Okay, so let's move to something a little bit different. I showed you that I can almost call them temporal heterogeneities in porosity because there's a dissolution process, affect the transport of a non-wetting fluid that is buoyant. What happens now if it's a spatial heterogeneity? So this is, you'll laugh because it has nothing to do with anything that you're looking at. This is just 100% melt, obviously. It doesn't have to be as drastic. So I will show you one extreme that I did for a different kind of case that has nothing to do with what we're talking about. But as long as you have a contrast in porosity that is fairly abrupt, it doesn't need to be in amplitude very large, we tested that, but it just needs to be sharp, decently sharp, then this process will happen. So this is a porous medium. I'm injecting the non-wetting fluid. This is without the crystals, and the colors here tell you a little bit about the velocity field at the pore scale. As soon as you reach this layer or this boundary where you lose this confinement by the solid, then these fingers break into bubbles. It's called a capillary pinch-off, right? It's something that a lot of people here at Cambridge have studied over the years. But you have a very interesting change in regime here. You have a continuous pathway that forms, takes a while, but then basically breaks into discrete bubbles that need to rise. So what I want to understand is how efficient is the transport of those non-wetting fluid here and here And the question I want to ask is whether it's more efficient for a bubble to transport through a porous medium than as a suspension. And the logic is here you have less obstacles and less friction potentially, so it should be a little bit easier. And we'll see it's the opposite. So coming back to the question you had, Rich, about confinement. These are two numerical calculations. They will cycle many times, so you'll see them a lot. Two numerical calculations. The red is the non-wetting fluid. You don't see the wetting fluid again. These are the solids in gray. The only difference between those two calculations is that I added some obstacle solids here on the sides. Okay? That's the only difference between those two. Same bond number, same everything else. And the difference is quite drastic. This one is able to stabilize a continuous pathway, right? And that's because of those solids here that prevent the inflation of the bubbles. Can you see this? The bubble here there's a constriction, so it cannot go through very easily. So it flattens as a gravity current, if you will. Well, there's surface tension as well, but it flattens. As it flattens, the amount of gravitational potential energy to go through the constriction actually diminishes. So you have the systems that are less stable if you don't have as much crystals. Okay? So that's what I call the effect of site confinement. So now if you take porous medium that are fairly simple, like those little networks that we played with, and you look at the flux of non-wetting fluid as function of the volume of bubbles that you jam into it, and you play with different random initial distribution of where the bubble should be, always in the same condition, dynamical conditions, then you find this is nothing new. When you don't have that much bubbles, I would not look at these values as good values, because that depends on the resolution. I'm not saying this is a perfect resolution kind of problem, but I just want to show the main point. When you don't have that much bubble, it's hard for the bubble to connect pathways, and most of the bubbles actually remain capillary trapped, so your flux is very low. And then suddenly you don't see the colors. I colored it differently, but basically you have a transition from here, and then you have another transition around here, I think. Anyways, here you transition to a stage that, depending on where, if you're lucky, where you put your bubbles initially, there are some cases that lead to continuous pathways that are stable over time, so you have a decent flux, and some cases where you're not lucky, right? It was not in the right place. And here, obviously, you have enough bubbles to basically build always connected pathways and have a decent amount of flux. The point here is that the flux of gas increases with the volume of bubbles, and that's something that everybody knows. It could be quite nonlinear as well. The problem of what happens above that layer, right? I started with a layer that had a porous medium in it, and then on top of it, there was a suspension with bubbles. Bubbles interact, as we saw, right, in the first few movies, and calculating how fast at low Reynolds number bubbles move up when they're buoyant, when there's a decent amount of bubbles around them, is not very simple. We did experiments. These are experiments with water, dyed in green, injected from the top because water is denser than silicone oil, in silicone oil of different viscosity. One of my students did that. The cool thing about trying to calculate the hindered ascent velocity, I don't know how you would call it, for those bubbles in the suspension, is that if you're in a low inertia regime, where you can neglect inertia, then the balance of force at steady state should be still between drag forces and the buoyancy forces. If that's the case, buoyancy forces, by having thousands of bubbles, if you know their size, is easy to calculate. The drag is not. So we can use this analogy between the two to calculate something. And this is what Sala did. What he found is that we need two correction functions to account for this ascent of bubbles as they communicate. The first one is a local term that takes into account the fact that if you have two bubbles, the first one, for example, the leading bubble is going this way, the trailing bubble follows and is aligned with gravity. Even at low Reynolds number, the second one will travel a little bit faster than what you would have expected from changes in velocity. So it reduces the effective drag. If now they're not exactly aligned, then the top bubble will tend to increase the drag on the second one, so make it slower. Okay, so this is basically what this term accounts for. Then there's another term that you need to account for. A bubble in a suspension doesn't feel that the surrounding fluid has the viscosity of the suspending fluid, but it's affected by the fact that there's other bubbles. So it's more like a rheology or effective viscosity. So we did those calculations and we closed the model, and this is what you get. Nothing really new there, but this is the relative velocity, if you think of it as such, of bubbles in the suspension as function of the volume fraction of bubbles. And this is a log scale in the x-axis. What you find here is that you don't need a lot of bubbles to really slow down the progression of those bubbles. So bubbles are afraid of crowd in some ways because you move slower and slower when you impact the bubbles. Here we take a system where there's no coalescence, right? We don't change the size of the bubbles as we increase their number, okay? That's something interesting. These are the experiments that we run. So now we have a system where you have a crystal-rich porous medium at the bottom. The more bubbles you have, the faster it goes. It's quite nonlinear, actually. And it's capped by a system where it's just a suspension. And the more bubbles you have, if there's not much coalescence, the slower they go. So it's quite interesting to think there might be a crossover when the more efficient of the two systems becomes a porous medium. And that's actually what we see. So those trends here, with this ugly green thing, are associated with the suspension, okay? What you're looking at here is the volumetric flux of this non-wetting fluid as a function of time. It takes a while to reach a steady state, and the reason why you have all this noise in the steady state is because we're losing bubble from the top. Right? So each time there's a bubble less, then basically you have a little bit of a jump. In all calculations we've done, we played with viscosity contrast between the two fluids of 1, so there's no contrast, I should say, rather, and all the way to 1 over 100. And we always find that the bubbles in the suspension, or the flux in the suspension, is lower than in the porous medium once you reach this stage. The second thing that we found, which kind of explains it to a large extent, is that when we play with different viscosity for the wetting fluid, it doesn't impact the transport of the non-wetting phase as long as you had time to build those channels. And that makes sense. If a non-wetting fluid percolates through a porous medium, once it formed this fingering pathway all the way through the porous medium, the wetting fluid is mostly a spectator of that, right? So it doesn't really dissipate any energy. It doesn't really move out of the way anymore. But that's not the case, obviously, for the suspension. In the suspension, you see a large effect associated with changing the viscosity of the ambient fluid. So here, for example, the viscosity contrast is 1, and here we increased the viscosity of the wetting fluid by a factor of 20 between these two calculations. So the greater the viscosity contrast between the two fluids, the biggest the difference in transport you have between these two systems, and the more accumulation of bubbles you'll have in the region that contains the smallest amount of crystals. And this is quite, to me at least, it was quite counterintuitive. One way to see that is that it's hard to build these pathways. But once you establish them, the energy dissipation, the rate of energy dissipation here, is governed by the non-wetting fluid moving through the system, because the wetting fluid is really a spectator. Now it's mostly passive. And the non-wetting fluid, we're always consider case, if you look at CO2 sequestration, if you look at magmatic systems with bubbles, always much less viscous than the surrounding fluid. But on the other hand, these poor bubbles, if they want to move up, they need to displace an equal amount of fluid in terms of volume out of their way. And that costs a lot of energy because the surrounding fluid, the wetting fluid, is very viscous. So you can have this tendency of accumulating gas where you would not expect to accumulate it. So the point I want to make here is that when you consider this three-phase system, there are lots of interesting things that start to appear at the pore scale that, at least for me, that I was not expecting, okay? Just as a warning.
Can you say a bit more about if you had, instead of a fluid on the top, you had a second
porous medium with a different porosity, but not as...
Yeah, so I think you made a statement that was basically, it doesn't matter how small that jump is, you just need a sharp boundary.
Yeah, so you want to elaborate on the sharp boundary?
And the size of the jump.
Okay. So for the dissolution problem, so where the porosity was evolving over time, we saw that the fingers that were very stable, in the same case without any dissolution, start to destabilize when you have about 1% dissolution. So my take is that a few percent of difference in porosity, you don't need to go to tens of percents in difference, will lead to this problem of pinch-off very easily. Now it depends. If the flux of gas that you have through the system is very large, it can probably build enough flux actually to go against that. So it really depends on how much bubbles you insert in the system, okay? You could be very critical just to have enough bubble to maintain those channels. In such a case, a little thing will destabilize them. But if you have a decent amount of flux to those channels, they will be a little bit better at handling the changes in porosity. if that makes any sense. That's the first answer. The second answer, the distance over which you want to see this gradation, it's not very clear, but it has to be on the scale of a few grains, or a few pores, I think. If it's on the scales, I think it could be a little bit larger than that, but you don't want the transition. Well, the transition, if it's very continuous, it's again, how much gas do you flux in? That's basically the same response as before. Okay, so it's always a balance on how much you provide, how much non-wetting fluid do you provide against it. Yeah.
It seems like there are three important length scales, and I wonder if there's any analysis possible of the relative sizes. One is the sort of capillary length scale that defines the stable size of bubbles.
Yeah.
The second is the kind of pore size, and a third is the throat size.
Yeah, that's what we're doing now, actually. So we're doing lots of calculation to see. There's another thing, actually, that plays a huge role. It only includes one of these times, the length scales. It's the bond number that you have. The bond number has a huge effect because it tells you how you respond. The surface tension, so the bond number will involve basically a capillary length.
Remind me what the bond number is.
Okay, so it's basically the balance between buoyancy stresses, or gravity if you want, so the difference in density between the two objects, and surface tension or capillary stresses. It has a huge impact on it. The viscosity ratio between the two fluids also plays a big role in the stability of those channels. So we're exploring a lot of the parameter space to get a better handle. But those are complicated systems, yeah. It's how fast can you grow the instability in some ways without recovering. That depends also on the contrast of viscosity. Yes?
So you got this flux of, I guess, that's a sort of macro scale flux you were showing in one of
integrated, yeah.
What would you do to get, or are you interested at all to get an equivalent of Darcy's law for these bubbles?
You mean in the, yeah, it's a volumetric flux.
Yeah, but how would it relate to, what are the driving forces at the macro scale? How would you relate them? Because you cannot use Darcy's law then.
You mean for
For the bubbles.
For the bubbles, the suspension part. Okay, so this part here. No, you don't use Darcy's flux for that. We just compare basically the amount of volume per unit time that goes across the surface.
Yeah, I
at this
realize
stage.
that, but I would say,
Yeah.
would you be interested to
It won't be easy.
smaller scale simulation? Let's say
Yeah.
I want to do macro scale simulation.
I'll show you how even much simpler problems going from the pore scale to the continuum scale is not simple. We talked a lot about volume averaging so far, and I will try to show you in some cases why volume averaging is not what nature does, obviously. Nature is more interested about some kind of conservation problems and optimization of thermodynamic principles than volume averaging. And so we'll see that in some cases it can play some dirty tricks. I'll be very careful volume averaging that, to be honest, if that answers your comment. All right, so
Before you, can I just ask?
Sure, go
does
for
it
it.
matter whether the matrix is static in your calculation?
yeah, in this case they're static. It does. The application we had in mind was relatively deep in a deep magma chamber, not too deep, but a few kilometers deep. If you have a soil and you do the same calculation, you need to account for the fact that the grains can move past each other. Especially if the pore space is fairly small, you have small constrictions, right? The amount of capillary pressure that you need to overcome for a bubble to move from one pore to the next is enough potentially to displace or deform the portion unit. That's not what we looked at. All right? All good? Okay, so the reason why I'm interested about the deformation of crystal-rich magma is, well, for people invested in magma chamber or magma dynamics, and there's a few of you here, you're interested about the rheology of magma is because it controls the rate of transport of magma, obviously. It also governs the rate of cooling of a magma reservoir, and to some extent, if you think of crystal fractionation as a big component for chemical differentiation, and Joe actually will talk a little bit more about that, I guess, then the viscosity is also fairly important for that. So, this is an example of a theory that is even simpler than everything that we talked about, because it's not even two-phase theory, it's a one-phase theory. It's an effective medium theory that is highly pathological at this stage, but that you can clean up fairly easily. That's kind of a good story, I think, before we start the more complicated ones. So this is some of the data that have been retrieved from experiments over the last 20 years. Obviously, it's not exhaustive. What you're looking at here is the relative viscosity. So that's the viscosity of the suspension with the crystals, normalized by the viscosity of the suspending fluid. So it basically tells you this function, how crystals or how adding particles into the system changes the viscosity of the system. Okay, this is the amount, the volume fraction of particles. So you all know, or most of you know this problem fairly well. At low volume fraction, actually, apparently it extends to much higher than what we thought initially, but experiments agree fairly well with the relationship that Einstein and Sutherland developed in about 100 years ago now, which is a linear relationship between those two variables. And all the data sets basically collapse that. So it's quite a self-similar kind of behavior. And the idea behind that is that if you have two crystals that are so far apart, they don't need really to know what the shape of the other one or the size of the other one is, because they don't really interact. So it's a relatively simple problem. But as you move along to higher crystal fractions, things get nasty. And so this is a semi-log plot, just to remind you. These are the same experiments run with the same material. The only difference here is the shear rate that is applied in the system. So you have a very high shear thinning kind of problems. In this case, about 2 orders of magnitude. Okay? So the question that we asked ourselves, actually, let me show you one more thing before I start that. So what people do in the magmatic literature right now is to use fitting curves like those ones to try to get a sense for what kind of viscosity you should use if they were looking at the crystal-rich magma. Now, this is highly problematic. First of all, those fitting curves have nothing in terms of process behind them, so it's very hard to understand what governs those different shapes. The second thing is, if one of you were to ask me what viscosity to use if you have a magma with 40% crystals, then you have about 3 orders of magnitude of variation here that you could use. Yes?
Could you repeat how the viscosity was obtained?
Sure.
These things, because
Yeah. So here what they do in most cases, they use basically rotating cylinders kind of like experiments.
you mean a Couette viscometer,
Yeah.
and they were identical viscometers, all with identical ratios, by the people doing them all.
Yeah, the real problem is not really the rheometer. There might be some cases where, for example, there could be some wall slip or things like that that could affect the results. But the real problem is the fact that the crystals here, the shapes matters. And the aspect ratio, the size distribution matters a lot when the particle can talk to each other. And they're comparing suspensions with widely different kind of styles of crystals in terms of shape and size distribution. And that's the biggest problem. And I'll show you how you can fix that actually relatively well. Any other question?
No. I mean, if you were to take, I hope I'm not delaying everything.
No.
If you were to take squares, presumably one experimenter
Yep.
with one class of crystals,
Mm-hmm.
and then another, it looks as though you're getting a series of relative jumps for particle volume fraction which have been observed elsewhere. And what you're telling me is that those jumps will be dependent upon the actual shape of the crystals.
What jump are you referring to?
Well,
When you go from here to here, for example?
yes, it's almost a jump. It's a,
Yeah, yeah.
but then it straightens out again.
Yeah, I will show you why I think this is the case.
Okay.
And I may not convince you, but at least I will try. So this I showed. So this is highly problematic. But this is a case of a system, even with an effective medium theory. So effective medium theory just means that you replace a two-phase system with a single phase that has magically, at least you hope, the same properties, right? So this is really simpler than everything that was talked about here. And the first thing that we did was look at the rheology literature in engineering when they look at spherical particles, okay? And so we developed a model for the relative viscosity theoretically. There's 2 variables that will enter here that were not expressed in the original laws that you may know of. This is the crowding factor omega. It's basically a measure of psi t is the maximum packing fraction of particles that you can have. So psi t will obviously depend on the shape, the size distribution of the particle, but also the shear rate that you have, okay? So omega is a measure of how this packing fraction will evolve under different conditions. And this other parameter, it's called intrinsic viscosity fairly frequently, is also telling you how if you play with different particles of different shape or size, they will affect the streamlines around them and have an effect on the effective rheology. Okay, that's kind of the idea. And this is a concept that was introduced by Einstein, for example, when he derived those equations. So with these two variables, what we argue is that you can basically introduce the effect of the microstructure, how the particles talk to each other. So we use them as state variables. And the first thing that comes up, we took these experiments that were published about 50 years ago. I forgot to put the reference. But they were run under different shear stresses. And what you see is that under these different shear stresses, both parameters vary, right? They both are depending on the shear that you apply. Here the shape, it's single size in spheres. What is interesting is that the product of the two, actually the ratio of the two, which is basically our exponent, is invariant in this case. It stays always the same. And so when you account for that, what you have is that all the data, if you rewrite them in terms of corrected variables that account for the crowding and the packing, and here this viscosity, you take basically this exponent on the other side, what you find is that all the data start to collapse on each other. You remove the effect of the shear rate. It's not that they don't depend on the shear rate, but these two variables depend and compensate for each other. And that's something that other people found in the 80s. That's not something really new. And we conducted that with different sets of experiments at different types of shear rate. It worked out perfectly well. Now, the effect of playing with the shape of the particle is very large on the packing fraction that you can attain before locking. And so we took a lot of experiments that were geared towards looking at packing under different conditions. And what you can find is for different aspect ratios. So here we use spheroids. So it's convenient because you have a single parameter to parameterize the shape of a particle, right? It's an ellipsoid of revolution. So it's a major axis versus one of the small axes. You have different types of particle, prolate and oblate. And what you find is from the experiments, a fit, so there's nothing glorious about that. But with this fit, now we can introduce the effect of the shape of the particle into our model. So it's a semi-empirical model. But when we do that, the data set that I showed you at the beginning that had some problems to it, it looks like that now. So there's some progress. The self-similarity to some extent has been retained. And so the effect that you saw, the difference between those curves, and that's only before you had this flattening plateau that you were talking about. The plateaus are still there, right? But those curves are basically homogenized. So there's a way to make them more unique by introducing this effect of the microstructure. And that works pretty well. So now you can start to make some predictions to it. There's still some work to be done, and we're still working on it, but I think it's quite encouraging that you can restore a little bit more use into those effective medium theory for that particular case. Now, the interesting point here is that 1 in this variable tells you that you have attained the maximum packing fraction, so you should be locked. And if we plot all this data with this, we find that there's some data that still have a finite viscosity above this maximum locking point, and they don't follow the same law. And what is cool is that this data set actually have shown that there's some subgrid, or I should not call it subgrid, but some shear localization to them. So we can diagnostic the cases that have shear localization fairly well with this model as well. This model should not work for shear localization, right? It's an effective medium, it's homogeneous, it should not account for it. So we can see, and one thing that was nice is when we did this analysis, one of those data points was not reported as having some problems with shear localization. It came out later, actually, in a different paper. So it's a kind of interesting diagnostic. All right, I will not talk about that, but this is how to account for polymodal size and correct for the Ferris model. But main point for rheology, this is a case where you had a wide spread of data, and you couldn't fix those problems of the microstructure in a very simple semi-empirical model. So it's relatively positive. But now we'll look at things that are much more negative. Let's look at the transport of chemical elements, the solid transport in a porous medium, especially consider heterogeneous porous media. And so we're working with some folks in Italy on this problem, and this is some of the experiments that they did. Here you have a tracer. It's inert. There's no chemical reaction in everything I will show you that's coming now. It's the simplest problem of a solid that doesn't react with the solid, but just transport through it. You see the sandbox, it's fairly large. You have 3 little lenses that have a different porosity and permeability, so lower porosity and permeability than everything else. As you will release this solute, you will basically travel through the system. That's what you see here. And you see these tails, basically, of the solute that was captured by these immobile regions, right? And this is very frequent for a remediation problem. That's basically what led us to work on that. Now, in all the models that we talked about this week, at some point, if you want to look at the chemistry, you need to use an advection dispersion equation with reactions, potentially. So let's look at how it does in a very simple system where you start to introduce some heterogeneities into it. And because we're talking about heterogeneous systems. So this is a calculation. Think of the whites. So the whites are solids. Think of this as more or less a microfluidics kind of calculation. The flow comes in. This is the velocity field. So I put some obstacles in the center to slow down the velocity. So here most of the transport through that system is diffusive, but it's mostly advective on the side. I want to see how these two batches communicate with each other. One thing that you look at is breakthrough curve. Is everybody familiar with breakthrough curves or effluent curves? Basically, at the outlet of your porous medium, you look at what comes out in terms of chemistry and you record that over time. Now, if at the inlet you inject a Gaussian distribution and you have an advection dispersion equation, the outlet is a Gaussian distribution, right? So this is a semi-log plot. Think of it as time. This is basically the concentration that comes out. And this is what comes out when advection and diffusion communicate and are more or less on the same time scale. Starts as a parabola, but then you have this very heavy tail. So most of the mass comes out much later, and it's just because it's trapped in these immobile layers. But you cannot model that with an advection dispersion model. There's no way you can do that. So this is yes?
Good if you add double porosity, for example.
Yeah, but then you need to basically adjust the rates between the two system. Yeah. So you need.
You have a double porosity.
Yeah, but
the middle was diffusing, right?
Yeah, but I'm not fitting for the rate of exchange. I'm solving for it. That's the difference. So this is basically what happens, right? You trap some of the chemicals in those low mobility regions, and then they basically come out later. Now, it's interesting to think about what are the conditions under which a transport of anything could be modeled by an advection dispersion or diffusion equation. So for a diffusion equation to be there, you need a problem that has stationarity, so your statistics are stable over time, right? That could be a problem for us, but in most cases, if you don't have much dissolution, you can think that might be okay. It should be a Markovian process, so it doesn't have memory. And that's a big problem in earth sciences, because in a natural heterogeneous medium, there's a coherence length for if you have a homogeneous, if you have like a batch that has a low mobility, and you do like a random walk step, it will be very short because the pore space, for example, is very short, is small. The next step might be small as well because you're in a batch that has a low permeability and low porosity. So there's a memory in a real porous medium for the transport of chemicals. And that's the biggest problem. The third problem actually is true too in natural heterogeneous system, is that you don't have an exponential distribution of mean free path or waiting times between consecutive random walk steps. And that's the reason why you don't have Brownian motion. You have a much more complicated system with a very heavy tail or complex dynamics. So those three conditions, at least two of them, and if you start to think about problems that evolve over time with compaction or dissolution of the porous medium, all three actually could be failing you to some extent, right? So you need to be careful with that. So why do we care? Well, we care because this is a very stupid calculation I did last week, just as a point for illustration. I model with a particle tracking method, so Lagrangian method, I model a breakthrough curve for a homogeneous system. So this is a parabola and a semi-log plot. And then I just did exactly the same calculation, so same amount of flux through the system, same dispersion, but I just added a batch you can communicate with that is immobile. So there's a probability for a particle to get stuck in this immobile region and to get unstuck later on. And that's basically finding the same kind of trend that I showed you before, these heavy tails, right? But now if you think that you have, this is a very long time, this is not a little quantum experiment, but if you're dumping initially at the beginning some radiogenic isotopes with some excess, the average time that the melt spends in contact with the solid, and this is not accounting for the fact that there's any reaction between the two, right? Because they can exchange isotopes. But it's very different, just because they don't spend the same amount of time in the system. But there's the same flux of material through the two, okay? So it's complicated to think about, but this heterogeneity can have a huge impact. And as we use geochemistry to infer the rate of transport of those melts in the mantle, because we don't have much more to do, it's very interesting to think about the effect of even small-scale heterogeneities, or relatively secondary heterogeneities, on how it will affect our interpretation of the melt transport in the system. There's ways to fix that, but it's more problematic. It's not with an advection dispersion equation that you will fix that. You can use, as Majid said, a little bit more complex models where there's communication between mobile and immobile regions, for example. You can use other models based on fractional calculus, which actually are quite nice. I don't know, any of you knows this problem of fractional calculus for mass transport? Hydrologists came up with it about 10 years ago to just look at these problems of breakthrough curves and other problems of sediment transport, for example. And the idea is that so I know we're in the Isaac Newton Institute, but Leibniz also played a role in calculus. Depending if you're German or British, you may have a different take on that. But we use still the notation of Leibniz, to be honest. But Leibniz also introduced at the same time fractional derivatives as an extension to the normal derivatives that we're used to. And people forgot about it for a long time because it doesn't make much sense. But it makes sense for conservation laws to some extent. And if you go back to the cases where you have random walk leading to a Brownian motion, if it doesn't lead to Brownian motion, the last point was you want an exponential distribution of mean free path and waiting times for Brownian motion and diffusion process. If it's a parallel relationship, then you have fractional calculus coming in. It's a natural outcome of the system. So it's not that far away from these conservation equations. And those fractional derivatives introduce a multi-scale nature into your equation at the continuum scale. So it's kind of a way to integrate subgrid scale kind of processes to some extent. The problem is they're not really used much more than just fitting kind of laws at this stage. But there's lots to be done with combining pore scale calculations with those types of approaches, for example. Other approaches, Lagrangian approaches, also can be quite successful for those.
Are you going to show us an example of fractional mass conservation law?
No, I can actually, but no.
Now that you've sold it, you should see it.
Yeah.
There's chalkboards everywhere.
I will not go there. So heat transfer now. I'll finish with the simplest problem of all of them that we see here. And I think Rich will talk about heat transfer tomorrow in those systems. I want just to take a homogeneous system, a porous medium, the equivalent of Rayleigh-Benard convection. So you have a hot plate at the bottom, a cold plate at the top, a homogeneous porous medium in between, and I will have two no-slip boundaries on the sides that are also adiabatic boundary conditions. Okay? So it's not an infinite layer horizontally. And I'll see if we can solve that problem. Okay? So the continuum equations, this is Darcy, and I will use an effective temperature equation, single temperature, by assuming that the solid and liquid at every point in my grid are in equilibrium with each other. So this is the mixture thermal inertia, if you will, and this is the conductivity of the mixture as well, and this is the inertia, thermal inertia associated with the fluid only. Okay? So the way we represent this kind of problems is by looking at the average heat transfer through the system as function of the forcing, the Rayleigh number. And actually, Anne was talking about the Rayleigh number before. This is a different kind of the Rayleigh number because it accounts for the fact that you have a permeable medium. It also corrects for the thermal properties of the mixture, to be honest. So you can approach this problem from linear stability analysis. You know that the onset of convection, so when the Nusselt number goes above 1, the heat transfer is not only conductive, it's about 4 pi squared. And then there's a nice relationship between the Nusselt number and the forcing. For me, the forcing will be the difference in temperature between the two plates. I will not play with anything else. Now, when you have a system like that, what you want to do, you want to test it experimentally. And this accounts for different thermal properties for the different constituents, so it should work fairly well. So what you're looking at here are data sets that were obtained, and there's many more that do the same thing. I just picked some data sets that look at still water, okay? And what you see is a delayed onset of convection by quite a bit, actually. And then a shallower relationship between heat transfer and the forcing, what you would expect. Now there's a few ways you can explain what the theory, the very simple theory that was put forward, should not work here. And I think the most logical is to say, well, steel and water don't have the same thermal properties, so you can fix within an effective medium theory, like you did, but you need to be a little bit careful there. It's possible that the two phases are not in thermal equilibrium, right? Steel conducts heat much faster than water. So there's an easy fix to that at the continuum scale still, is to say, well, now I have two temperature equations, two energy equations, one for the fluid, one for the solid, and they talk to each other when they're co-located through a heat transfer coefficient. And you have more complicated, we played also with more complicated two temperature equations. Those are called LTNE models, local thermal non-equilibrium models. Okay, so see if it fits it. When you use these models, what you find is that the onset of convection from linear stability analysis is earlier, and the amount of heat transfer you have out of it is faster. The more disequilibrium you have, the further away you go from there. So it doesn't really fix your problem. Actually, it makes it worse. The other thing you can do is do the linear stability analysis and compare the convective motion of the modes that are excited just above the critical Rayleigh number with the one that you see either experimentally or from pore scale calculations. And what you find is that they're wrong. They're not the right ones. So there's a problem on how we do at the continuum scale this heat transfer in the porous medium to some extent. Okay? So let's see if we can do it at the pore scale correctly. So these are calculations that we've done with one of my PhD students. So Hamed here is solving for the fluid dynamics. The heat transfer between the two phases, we use the conjugate heat transfer boundary condition between the two phases.
The flow is just in the channels?
No, this is just convection, so this is a single mode, right? The first mode.
And is this a porous
Oh,
medium?
yeah, sorry.
Solid block?
Yeah, I'm showing temperature, but here there's no flow. Totally right. The squares are solid, yeah. And so this case is below the critical Rayleigh number, and the Rayleigh number increases as you move here. So we played with relatively small Rayleigh numbers.
And they're not in equilibrium with each other?
They don't have to.
What's the
Here
relative
they are, but they
conductivity?
are.
They're very close. And that's one of the main points, that this behavior happens where they're basically in equilibrium, more or less.
What's the relative conductivity of the fluid versus solid?
We use the same as steel and water, 50. And that's what you find when you do those calculations. So it solves a lot of these issues. We have a delayed convection, and then the parallel is much lower. So there's something that is lost when you go from the pore scale to the large scale. We're working on it. It's associated with the scale of the circulation, actually, in convection. When you have a thermal contrast that is relatively large, like this one, you have a lot of small scale circulation around those grains that don't really contribute that much to the heat transfer over the scale of the whole domain. So you break down the energy basically under different kind of scales. So that's the reason why it does that. Yes?
Yes, but if you depend on the scale of your pore compared to the
Yeah, we run lots of calculation with different size and we find the same results. But it's a very good comment. It's one of the dimensionless numbers you want to play with, right? Yeah. So it's a simple problem, right? But there's a way to fix that, I think, at the continuum scale. We need to introduce some corrections that depend on the Pechlin number on the dispersion tensor, I think, and that might be one way to fix it. But it's not very clear. It's still something to work on. And if you think of it, this should not cause too many problems, right? This is really the bread and butter. So this is a problem only when the thermal properties are not the same, okay? But when they start to depart from each other, it starts to become a problem. All right, so I think I've talked almost enough. So now I will conclude. So, obviously, this is just stupid because everybody knows that. Upscaling to continuum approaches is difficult, obviously. Upscaling means and requires a loss of information, right? That's kind of the point of upscaling, actually. You want to make the problem more extractable. But you need to be careful what information that you're losing. And sometimes doing small-scale calculations or experiments in the lab is just a way to test what you can leave out and rebuild sometimes. The last one I would like to emphasize is we have a tendency, all of us, to homogenize things in terms of volumetric average because it's a natural thing to do for us. But I don't think nature operates like that. You know, for those of you who have worked on principles of least action and things like that, nature operates in a different way. It optimizes thermodynamically, basically, its path to do something very often. Not always, but very often. So we should try to think about ways to upscale that is a little bit more consistent with a thermodynamical framework instead of just the volume average. And I think that will help a lot of these issues. Now I'm saying that, I don't really know how to start. I'm working on it. But this is a difficult problem, but I think that's basically part of the clue on how to build a good continuum scale model. I'm not saying that continuum scale models have no value. They have a lot of value. But there's a little bit the danger sometimes. I think that's it.
You said about upscaling more from point of averaging, but there is so-called upscaling machinery from low scale to higher scale, where we take into account actually blocks and
Yeah, totally.
in this case the question is not just averaging.
Yeah.
So you are changing your effective permeability and distribution. Instead of actually having a scalar, you will have a tensor permeability. So
Yeah, but yeah. So, but even defining a permeability, for example, is based on porosity. You're basically assuming some volume average behind it. I'm not saying having anisotropy is fine, and this is a good way to.
but, you will end up with anisotropy. You
Yeah.
will start with homogeneous, but you will end up not homogeneous, but isotropical, but you will end up with anisotropic
Yeah.
tensor.
Yeah, it's like if you have a layered porous medium, for example, you flow this way or this way. You have, but it's good to have difference if it's correct, right? That's my point. If you basically do the volume average instead of basically look at the direction of the flow compared to the strata that have different conductivity, if you just do the volume average and don't think about the fact that it could be anisotropy, you will make it wrong in both cases.
I'll ask a question.
Yeah.
Do you think that it's as much a problem with homogenization as it is the fact that we often have trouble knowing what the interface and what the interaction is at the interface? Because John talked about in his first lecture, we have to write down some constitutive laws with regard to how momentum and energy and things like this are transferred at the interface. And these are often just based on invariance principles and things like this, just to avoid, violating Galilean invariance or objectivity or second law of thermodynamics or whatever. But they're crude, since we often don't always know what the interface looks like.
I think it's the same problem to me. It's exactly the same issue, but looked at two different standpoints. So you look at this issue from the continuum scale and try to introduce basically subgrid kind of interfaces. And I'm looking at it from the pore scale, try to find a way to get to your continuum scale. But I think it's exactly the same issue. I'm convinced that this is the issue, really. Is, for example, when Majid was talking about this new Darcy equation, right, or the correction to Darcy equation, the generation of interfaces, which is a great idea because that's truly where the energy goes to. But how do you solve for it and know exactly what kind of model to put in there? And that's the issue, right?
But I wouldn't call that a homogenization problem. That's more of a, right, trying to understand what the constitutive law is for things like drag and pressure work and things like this at the interface without knowing what the morphology of the interface is exactly. Well, you can at least write down the morphology, or you can state it. That's squares or whatever. Okay, sorry. Question in the back.
Maybe a question for coffee break is, I have a little problem with the logic of the last conclusion, to use that as an argument pro or con averaging. Nature doesn't do any averaging. Nature doesn't know what permeability is, what viscosity is. These are all tools in order to describe things, and you need them because, like you did, you want to work with an average flux. You don't want to measure flux in every single
the error
pore.
is not, the averaging is coming from us. What I meant here is basically that when we do the averaging, basically because we want to look at the macroscopic quantity, for example, we sometimes don't follow the rules that we should follow. So think about it this way. But, for somebody was showing, for example, tomographic data, it's a good example, right? Just the waves basically passing through, if you believe them, then they basically do a natural upscaling to some extent, right? So how do you interpret that? It's not easy.
More questions at all? Yeah,
Mark.
Can you throw up the convection picture just one more time? Just a comment.
This guy?
Okay. Yeah, I mean that's really nice, but I think the other point to say is that the continuous upscaled equations of that are really poor approximation.
Yeah.
Because Q is not a continuous field there. It's 0 and 1 on the scale of your temperature gradients. So I'm just curious if we can take those blocks down to epsilon, smaller than the thermal boundary layer scales, it should go to the continuum solution.
So we tried with, we're limited in terms of size we can play with, right?
Oh, I understand.
But we tried with size that range quite a bit, and actually we find the same kind of consistent results.
It's just that those are actually of the scale of the thermal.
Sure, But the one thing that is interesting, for example, is that we follow exactly, when we do those same calculation but the conductivity ratio is 1, we're perfectly on this line. So with the model that you see, if the conductivity ratio is not changing between the fluid and solid, we're basically doing the local thermal equilibrium method is perfectly fine. We basically retrieve exactly that law. And that's what we tested first to see, okay, what do we have some kind of an REV that is potable, actually, so we can export some data. And we're perfect on it. So the problem comes because you have a contrast in thermal properties. And it's hard to deal with that because that brings up the interface just right out.
Right, but that's it. But it's,
Yeah.
what I'm saying is that those continuum equations are really quite a bad
Oh, yeah, yeah.
model.
Yeah, totally. Yeah.
But when you even did the problem of allowing two different temperatures in each medium and you had some transfer coefficient, I mean, what did you choose for the transfer coefficient? You showed one case it just failed, but you have another.
They all fail.
No matter what you use for little h.
So if h is infinite, you're here, and as h decreases, you go this way. Because if h is infinite, you have thermal equilibrium between the two phases.
Yeah, I understand the physics of this. If the grain size is very small compared with anything else, and its thermal equilibrium time is short compared with anything, then what goes wrong? Why doesn't that continuum model work?
If the thermal, so we're working on that. It's not a simple problem.
Why not? What is it that goes wrong with the physics?
Well, actually, let me show you one thing.
That's what I don't think I've understood. I don't think Mark has understood.
Let me show you one thing. So it's kind of an ugly plot, but it shows you the magnitude of the velocity field. I don't have the scale bars, but for different cases. So this is a case where no convection, you increase convection. That's where the case where the fluid and the solid have the same conductivity. Okay?
Yeah, but this is terribly coarse grains.
Yeah, sure.
I mean, if I made them 100th of those,
Mm-hmm.
right, so that actually the percolation and everything was on the scale, which
I don't think it's a problem of scale. Because, first of all, we played with bigger domains, not that go much
explain to
beyond.
me what's wrong with the physics,
Yeah,
rather than saying that you've done some experiments and it doesn't work.
that's what I'm about to show you.
When
So look at this one. This is when the conductivity is the same. And we conduct the same calculation, but the conductivity are not the same. You have much more circulation around the grains.
but your grains are so big,
But they're the same size in both cases. That doesn't matter.
but they're so big compared with the process you're looking at. I mean, I can quite believe that you can't upscale when your grains are as big as this. But now make them a
No, we
100th
can
of this.
upscale. I just showed you that we can upscale. To answer Mark's question, I just showed you that if the conductivity are the same in the previous case, we fall exactly on the law that you predict at the continuum scale.
Can I ask, just as a point of clarification on this slide, what's your definition of the Rayleigh number in terms of the thermal conductivities? And have you taken these measurements as a statistical steady state?
Yeah. So second answer, yes. First answer, what we do first of all is calculate the conductivity. So we do the same calculation with no advection. Okay. So it's a purely diffusive problem with exactly the same properties. And we get at the steady state what the effective conductivity of the two medium is. Because that's the real one actually that you need to use. Okay? Because it's a mixture property in those equations. And that's what we use to calculate the Rayleigh number in the thermal properties. You see what I mean? So you conduct this calculation with this, like in the same regime here where you have no convection at all. And you can calculate what the effective thermal conductivity of the system is at steady state. Yeah.
I want to come back to what Dan and Mark were saying because it
Mhm.
seems quite clear that if you have circulation around a grain,
Mhm. It
then-
depends on the size of the grain. Yeah.
Yeah, you're never going to find a continuum above that length scale. You have thermal gradients across the grain, which drive buoyancy gradients across the grain, drive circulation across the grain. You can't homogenize that.
So
The physics that you're interested in is at a smaller scale than a representative volume element that includes many grains. It's just not a problem that can be made continuous.
But my point is not to say that you can upscale those problems at the ratio of k is 50 doing exactly the same method. Actually, my point was to show that when you change the conductivity ratio, things that you could upscale easily before that was working, we were exactly on the right curve, just start to fail, right? Now, we're doing experiments in the lab right now with an IR camera to test those kind of things experimentally in the lab. It's also very interesting to see that people have tried many, many ways to get all the data sets that are calculated experimentally in the lab. That just deviates from that. And it deviates from that experimentally on big columns only when they play with conductivity ratio or not 1. And try to fix that with a slew of different problems, including looking into this kind of corrections for 2 temperature models and so forth. It doesn't work. And this is a fact, right? So what we're trying to get at is a way to...
The grain size, there must be a limit where the grain size has gone smaller.
Well, but it won't be around 1 grain that you will have circulation, but it will be around n grains that you'll have circulation. But you'll still have some small scale circulation that you're not resolving. That's my point. I don't care if it's circulating around a single grain or an aggregate of tens or hundreds of grains, but you change the scale over which the circulation happens. That's my point.
You describe the experiment, these red diamonds and squares. What are the grains? I mean, in the experiments themselves.
The experiment
what's
themselves.
the porous medium like?
So those ones are very controlled. They look very close to what we did numerically.
Oh, okay. So these are huge grains.
Yeah, those calculations. Yeah. So that's the reason why we did the scales at the pore scale for those.
This is what these guys have a problem with, which is,
Yeah, but there's experiments where it's much bigger, and they find also that the trains are basically bent down, actually, the same way.
There's experiments when there's what?
Where they take bigger domains.
Bigger domains of more porous.
Yeah, so either that you have much more grains into your domains, or they basically the grain size is smaller. And they found also the same deflection when the conductivity rate is
But I
normal.
think it's also a question of how many grains there are relative to things like the thermal boundary layer.
Yeah.
Yeah.
Scale.
Yeah.
Well, that's the thing, is if you have a finite number of grains within a natural length scale, like a thermal boundary layer or something, then the continuum approximation is obviously going to be.
Yeah, no, totally agree.
So the question Dan asks is, if you have something that's realistic grains, grains that are
Yeah, much smaller than the boundary
millimeter
layer. Yeah, there would be.
with large boundary layers, where is there a failure with that?
It's not, I mean, a bit more than that.
Sure.
That also the timescales for the equilibration must also be very short.
Right, and that would happen with a very small grain.
Depends on content.
Yeah, right.
But I mean, everything satisfying the continuum approximation. Then where does it go wrong? And what you came back with was that, if you do that, then your porosity is no longer uniform. Well, that's fine. I mean, of course that won't then upscale. If your porosity, permeability relations vary within your region, then of course you can't upscale it. But that's not really the point. The point is that if that is not the case, so the permeability is uniform, that the scales are all small compared with anything else, then where is it that the physics goes wrong? That's the bit I haven't understood. You can't have local circulation, as you said. You can't have time dependence, right? Because all of that is ruled out by the conditions which I just said. So what is it that then goes wrong? Or is it that the experiments are just simply not satisfying those?
So my argument is that when the conductivity ratio between the solid and the fluids are not the same, well, when they're not 1, what starts to happen is that the dispersion coefficient for the temperature that you will introduce in those continuum scale equation, because you need to introduce dispersion as well at the continuum scale, needs to depend on the Pecklin number, and the models that we have so far don't work very well.
But you've just already thrown out the crucial one, which is that assumed in the upscaling that the thermal time constant of each grain is very short compared with anything else. Obviously, if that isn't true, then you're not going to be able to do a continuum model. So if you say, but it isn't short, then I would say, well, no, of course you are not going to be able to do a continuum. I haven't understood at all yet where the physics is.
But
Let me just stop.
no, just one comment actually.
Go ahead. I don't want to.
I want
get
to
the
just
last word.
Yeah. The two systems actually are in equilibrium locally, thermal equilibrium. Even for the case where the conductivity ratio is 50. We looked at that. So it has nothing to do with the fact that the thermal response of the solid is very slow. That's not the part of the problem. Because that we tested.
Okay, we should have a coffee break and thank the speaker.